this lesson, we introduce transmission lines, and we start with a time domain analysis in which, therefore, the quantities that we see are functions of space, but also of time. So in standard circuit theory, the circuit can be as complex as desired, but the size, the physical size of the circuit is zero. What we want to introduce by the concept of transmission line is, at least in some dimension, in a unique dimension, a finite size for the circuit. For instance, you have a source, like in this slide, and you have a load, or L, that is shown here, and they are connected by two wires, by something that necessarily, by the physics of electromagnetics, has a finite length. And by the physics of electromagnetics, this implies a finite delay in the propagation of the voltage produced by the source to reach the load. So the voltage produced by this source is a function of time. Let's suppose that is this white shape that you see here. And normally, when we deal with the circuits with moderate size, we can neglect these delays. As you see, we are in the condition of tau 1 that you see here in this picture. There is a small delay, so that the function produced by the source is not exactly the same as if it were a direct connection between this load and this source, but there is a small delay. This condition, the delay, let's say, that is normally neglected. But if this is not so, so if the delay is comparable to the transients of the source, in this case, as you see, the delay tau 2 is very, very large as compared to tau 1, and is comparable to the transient of this source. In this case, we cannot neglect the presence of a delay. Normally, in air, electromagnetic waves travel at a speed of 30 centimeters per nanosecond. This means that depending on the size, on the length of this transmission line, the two wires connecting the source to the load, there will be a negligible or non-negligible delay. So that what we want to study now is the presence in this transmission line of waves that represent the propagation of the quantities related to circuits, currents, and voltages from the source, from one point of the line, of the transmission line, to another point, for instance, from the source to the load. Of course, associated to the voltage difference between the two conductors and to the current that flows in opposite direction in the two conductors, there will be some fields. Therefore, the voltage is associated to the presence of an electric field and an electrical induction field, and the relationship between voltage and field is the well-known line integral, so that the voltage difference from 2 to 1 is minus the line integral of the electric field along any line that connects conductor 1 to conductor 2. Similarly, the magnetic field is associated to the circulation of the circulation of magnetic field is associated to the current, so that there is a direct link between the current and the magnetic field, as shown here. And we see the flux lines of magnetic field in blue, electric field in orange, and their relationship with voltage and current. So that whenever we speak of voltage and currents, we also mean that there is an associated field with them. And of course, since we are dealing with electromagnetic waves, there is not a single wave of a single quantity V voltage, but there is always both terms, V and I, E and H. So, in order to study, what we keep in mind is that there is a relationship between charge and voltage that we have studied from electrostatics. So we consider a small section of transmission line of length dz, to which we apply a small voltage difference, V. Of course, this small section of transmission line will be associated to the presence of a charge, a positive charge on the positive conductor and a negative charge on the negative conductor. The charge on this small section dz equals the charge per unit length Q, capital Q, times the length dz, so that these two charges correspond to the presence of this voltage difference. And they are linked by a quantity that we know very well from electrostatics, is the capacitance, and in particular the capacitance per unit length, so that the charge per unit length times the length equals the capacitance per unit length times the length times the voltage difference. Similarly, we have studied the concept of inductance, and specifically when there are two wires on which there is a current that flows in opposite direction, we can plot, as you see here, a surface and a boundary to this surface and compute the flux of the magnetic induction through this boundary and associate this flux to the current by the concept of inductance. So that associated to a small length dz of line, there will be a flux per unit length phi times dz. Phi is the flux per unit length that must equal the inductance per unit length times dz times the current. So that there is also in this case a link between fields and circuit quantity, voltage and current. Okay, now let's switch to what happens in the longitudinal direction when we introduce the time dependency. So that we see that, as you see in this picture, the circulation of E must equal by Faraday's law to the negative of the time derivative of the flux of B. And we apply this relationship to this circuit. So we compute the circulation of E around the orange line, and we associate it to minus the time derivative of the flux of B through the surface whose boundary is the orange line. And we see that the relationship between the direction of the circulation and the normal to the surface that corresponds to this flux. Now, as you see, this circulation of E is non-zero only at the beginning and on the end, because on these two segments, horizontal segments, the tangential component of electric field is zero. We are in contact with the conductor, so this contribution vanishes because of the zero of the electric field. But in these two segments, vertical segments in the picture, there is a non-zero contribution. And this contribution corresponds, as you see, to the voltage, so that we can compute that the voltage computed at Z plus dZ minus the voltage computed at Z, and this is the result of this circulation, the left-hand member in this equation, must equal minus the time derivative of the flux through this surface, which is the flux per unit length times dZ. Of course, we can substitute in place of this difference by the differential theorem. This difference can be expressed as the partial derivative of the voltage with respect to Z times dZ. And this becomes the left-hand member, whereas the right-hand member, once we substitute in place of phi L times I, as you see, we obtain the first equation of the transmission line that corresponds to Faraday's law. This equation states that the partial derivative of the voltage with respect to Z, to the direction of the line, equals minus L, the inductance per unit length, times the derivative, partial derivative of I, the current, with respect to time. The second equation that we use is the other Maxwell's equation that states that the circulation of H through a closed boundary equals the total current flowing through the boundary plus the flux, the time derivative of the flux of the electrical induction through the surface, whose boundary is the line on which we carry the circulation. Now, we take a very special line. So we apply this equation, with this Ampere-Maxwell's equation, to this red line that you see here plotted. And specifically, this red line corresponds to three surfaces. As you see, we can run on this, go back here, carry out the circulation around this cylinder. When we go back, and the circulation on this, and this entails the surface that is plotted in white, bluish color here. So there is one contribution that corresponds to this circulation over the whole of these lines, and that corresponds to the flux in the right-hand term. We have to do the total current flowing through this surface plus the flux of D. But this circulation also equals, as you see, since these two terms that you see are run in different directions, these two terms cancel, so that this total circulation, the same value of the circulation, also corresponds to the flux through this surface in gray here, and that surface in gray, which is not shown really, but is on the other side of the wire, on the other side of the line, at the distance dz from the first one. So that the same value of the circulation must equal, on the first surface, bluish the result of the right-hand term, and on the two surfaces, let's say gray, the result of the right-hand term. So let's compute these two different terms. As you see, once we compute the flux, the right-hand term of this equation through the bluish surface, there is no current flowing inside this surface, but there is a flux of D, because we know that this corresponds to the direction of the electric field. So there is a non-zero flux through the bluish surface, but zero current. But on the gray surface, there is no flux of D, there is just the contribution of the current. So we can equate the same value of the circulation on the left hand to the two values of the right-hand member. On the gray surfaces, we only have a current, and so we have a difference between two terms. The current computed on one side, this side, and the current computed on this side. This same right-hand member, for the same value of circulation but computed around the surface in bluish, gives the flux of D. And this flux of D equals minus the time derivative, partial derivative, of the charge per unit length times dz. So this is the result of Ampere's-Maxwell's equations once we substitute their expression, the expression in terms of currents and voltages, as we see, because the charge per unit length equals the capacitance per unit length times the voltage. So that we can substitute furtherly into this right-hand member the capacitance per unit length times the voltage times dz, that substitutes this, and so we have this contribution, and the C is here, and then the left-hand term, by the differential theorem, can be substituted with the partial derivative of the current with respect to Z times dz. There is a simplification of dz also in this case, and we obtain as an equivalent of Ampere-Maxwell's equation this second transmission line equation. Sometimes these two equations are called telegraph equations. So we have therefore that, as you see, first equation that corresponds to Faraday's law, see back here, it is repeated here for your convenience, and second equation, Ampere-Maxwell's law, that is plotted here, and we apply a second derivative, another Z derivative to this. So as you see, we derive with respect to Z the first equation and also the second equation. We obtain here the second derivative of V and I with respect to Z, and here we have a mixed derivatives of the other quantity with respect to time and space. Once we obtain this, we can change the two derivatives, and so we can substitute in place of these derivatives a time derivative multiplied times C. What you obtain is the so-called wave equation for the voltage and for the currents. The wave equation are this one. As you see, we have substituted one derivative thanks to these equations in this term. So we have two wave equations for voltages, for voltage and currents, that represents the propagation, because the solution of these two equations can be expressed as waves, something that propagates without distortion along the line itself. And specifically, the general solution to this wave equation for V is the sum of two functions that are completely different functions, arbitrary functions, but the important thing is that they are functions of variables Z minus V times t, in which V is the speed at which they travel along the transmission line. By substitution, we obtain that V, the speed, is 1 over the square root of LC. As you see, A plus is this function, whatever function, it propagates in the positive Z direction. A minus is another function, arbitrary, but a function of Z plus V times t. So with the positive V, this travels in the negative Z direction, and is plotted here. Similarly, a similar equation we have for I, in which we have, for instance, a function B plus and B minus. But let's not forget that V and I are linked by first order equation that is here, so that we now substitute. Because what we want to find is the relationship between V and I. We know that this relationship exists because we are in the presence of electromagnetic waves. We want to find the expression. For this reason, we carry out some derivatives. We can see and follow all these passages slowly by looking back at this video and also at the text. But the result is that v and I, for a single wave that travels in one of the two possible directions, for instance, the positive direction, are linked by a constant. So that the general solution for v, for the voltage, is an arbitrary function that propagates in the positive z direction, and the general solution for I is the same function but divided by the quantity zc. That c as this expression, the square root of L over c, is called characteristic impedance. So the single wave that propagates in the positive z direction is composed of a voltage wave and a current wave. They travel together with a constant ratio between them, and this ratio is called characteristic impedance. Similarly, the negative wave, the wave that travels the negative z direction, has the same arbitrary function of z plus v times t and divided by zc, but the difference is this minus because the wave travels in the opposite direction. So if we keep the same sign for the voltage, we'll have to change the sign for the current.